Hello guys, in this lecture we're going to look into the inverse dynamics of robotic manipulators. With inverse dynamics, the goal is to be able to find the torques and the forces inside, the motors. For example, here we have a three-link robot. The first, we have T1 here, T2, and then T3 are the torques that are moving that robot. And we could also have forces in the X, and then the Y, and then in the Z. And the main question here in inverse dynamics is, given that we have a particular path on the end effector, right? We can use the inverse kinematics to find theta 1, theta 2, theta 3 as a function of time. So we assume that we know the position of the robot as a function of time, and then we are trying to solve for the forces and torques that are creating that motion. So basically, you are doing F is equal to ma, but you are doing on this, a multi-body system. The number of unknowns that we are going to have is going to be equal. So on the first link, how many unknowns do we have? So we have fx, for example, we have fy, and then we have a torque, right? And because this is a planar robot, how many equations can we have? We can have we can have the forces, summation of the forces in x direction, summation of the forces in y direction, and then we can sum the torques, right? So we have three equations and then three unknowns. And in total, we have three links. So how many equations are we going to have? We're going to have 9 equations, right? How many unknowns are we going to have? We're going to have 9 unknowns, right? So we have 3 unknowns on the first one. Like I said, torque, fx, fy. Here we're going to have torque, fx, fy. And the fx, fy here are going to be equal and opposite on both links. So we have 3 unknowns, and then 3 unknowns, right? So we're going to have 9 equations and then 9 unknowns. And if you have any external load on here, you also need to know that load, right, to be able to solve these equations. All right, so how do we solve that? So on one diagram, we're going to have the forces. On the other diagram, we're going to have the accelerations. How do we do the accelerations? So basically, we have to find the accelerations of the center of gravities of all the links. So here we have MAG1, and then we have IG alpha. So every rigid body will have MAG at the center of gravity. So this is my inertial force, and then it's going to have IG alpha, where IG1 is the moment of inertia about the center of gravity. Alpha 1 is the absolute angular acceleration of this link. In this case, it's going to be theta 1 double dot. And on the second link, my free body diagram, or my inertial diagram, is going to have MAG2, where AG2 is the acceleration of the center of gravity of the second link, and IG2 alpha 2, where IG2 is a moment of inertia of the second link about its center of gravity, and then alpha 2 is its absolute angular acceleration. So in this case, alpha 2 is equal to theta 2 double dot. Is that true or no? It's not true. Why? Because theta 2 is not an absolute angle. It's not an absolute angle. For this to be an absolute angle, it has to be measured with respect to a non-moving frame. So therefore, alpha 2 is going to be equal to theta 2 plus theta 1, right? So you would need to capture alpha 2 with respect to x0, right? Because x0 is not moving, whereas x1 is moving. So on and so forth. So let's go into this third slide, basically. So here what I have is a procedures for you to be able to do the inverse dynamics of any robot. The first thing that you need to do is you need to calculate acceleration vector at the center of gravity of every link. So you would have a robot, you will identify the center of gravities on all these links, and then you need to find the acceleration vector, which contains acceleration in x direction and the acceleration along the y direction. Step 2, you need to draw a free body diagram of all the external forces and moments which are applied on every link. Step 3, you will equate the forces. So whatever forces you have in x direction has to be equal to MAGX, right? You have so many points on that rigid body, right? We're only interested in acceleration of the center of gravity, right? Lastly, we're going to solve the equations, right? So we're going to have, the number of equations must be equal to the number of unknowns. We can put that in a nice and clean matrix form, and then we're going to solve for the unknowns. What I'm gonna do is I'm gonna do a basic example on a 2 degrees of freedom robot that we have been playing with for a while now. So let's do that. So let's look into our robot. So this is my first link. This is my second link, and this is my data 1. And this is my data 2. And let's say the link lenses are L1 and L2. And now we're talking about dynamics. So I'm going to tell you that the first link has a mass M1. Second link has a mass M2. Moment of inertia of the first link about the center of gravity, which is here in the middle. Let's assume it's uniform. So this guy is G2. And we have I1 is the moment of inertia of the first link about point G1, and I2 is the moment of inertia of the second link about point G2. So my question to you guys right now is find me the inverse dynamics of this robot. Let's say, this robot is, going along like a particular path, right? It's, traveling through this point. And as a result of this movement, it actually has, we know theta 1 as a function of time. So this is known, right? Theta 1 as a function of time is provided. We also know theta 1 prime as a function of time by differentiating this guy. And we also have theta 1 double dot as a function of time. So this is my alpha 1, right? And we also have theta 2 as a function of time. We have theta 2 prime as a function of time, and then we have theta 2 double dot as a function of time. All right. So what is alpha 2? Alpha 2 is going to be equal to theta 1 double dot plus theta 2 double dot, because this guy is the absolute angular acceleration of the second link, right? And so the absolute angle is with respect to this line. So it's theta 1 plus theta 2, right? Differentiate those 2 times, you're going to get alpha 2, right? This is very important, when Newton's second law was derived, F is equal to ma. A has to be measured with respect to a fixed frame, right? So if you are trying to find the force, total force that, the wheels are applying on a car to push it forward, you have to measure the acceleration of the car with respect to a non-moving frame. Like you can't be sitting on a different car and then measuring the acceleration. You have to be on a static frame or a fixed frame. All right. So those of you who have taken dynamics with me, we have went over this in very detail, right? So this is the reason why we actually have to have alpha 2 to be an absolute angular acceleration. All right. So what I will do is we're going to apply the steps that I just illustrated. So I'm going to come back to my slide. All right, so what do we do first is we're going to find the acceleration vector of the center of gravity. Now I'm going to draw a free body diagram. Although I have these steps like that, I prefer if you actually will do them together. Let's do a free body diagram first, just to understand what we actually have here, right? So let's do a free body diagram. On the first link, so what are the forces on the first link? Well, we have a motor, right, that is trying to push it with some torque. And then here basically I'm assuming the torque is like that, right? And then ultimately if I solve T1 and then the value of T1 was minus 0.5 or minus 2, then it would be the opposite of what I've assumed it, right? And then if the final value of T1 is positive, it means that, yeah, my guess was actually right. And so this is the first unknown, and then obviously this is hinged, right? Or the motor basically has to be fixed. So you actually have some forces here, right? So usually I like to label the forces based on the frame. So I'm going to just call it OX in that direction, and I have OY. All right. What else do we have? Well, this guy has a center of gravity. It has dimensions. So it has material on it. So it has a weight. And I'm going to do M1G, where M1 is the mass of that link. And basically, because that link is actually interacting with another link, so what we actually have, we have some other forces here, and I'm going to call this O1X, right? O1X, and I have O1Y. Now, there is a torque basically that the motor that is driving the second link is actually on this link, right? And if you try to hold the shaft of the motor, the housing of the motor will have equal and opposite torque, right? So if this motor is trying to apply torque like that on the other one, right, then what will happen is that the other motor will apply an equal and opposite torque, right? So we're gonna have my T2 is gonna be like this, right? As a result of this motor trying to push the other link. Does that make sense? Okay, so this is basically the free body diagram. And now let's put the accelerations. And on acceleration, all that I really care about, no matter how the geometry of this, how weird the geometry is, let's actually assume like, has some really weird geometry, you have holes, etc. We're really simplifying it as a link. And this is the center of gravity of it. And I'm assuming the center of gravity here is in the middle. It could be anywhere, right? So all you have to do is just find the acceleration on the center of gravity. For simplicity, we're assuming it's on the middle. Center of gravity, we're going to have what? M A G1X. I'm going to call it M1. M1 A G1X. And in the vertical direction, we're going to have M1 A G1Y. Right? So this is the forces. Something the forces in X will give you this. Something the forces in the Y direction will give you that. And as a result of the forces being applied at some offsets, you will actually have a rotational inertia, and then we call this one I G1 alpha. So here it's always IG1 moment of inertia of this guy with respect to the center of gravity about this axis, like an axis through the pin, right? So IG1 alpha. Okay. Let's quickly do the free body diagram on the second link, and I'm gonna move it slightly up. Okay, so on the second link, basically, let's assume it's like that. What are the forces? So Newton's third law of motion tells us that you have equal and opposite forces between interacting bodies, right? So if this guy is, so these are the external forces on this. So if the external force of it, if something is pulling it with O1x, then this guy is going to be, then this guy is pulling it on the other direction. So we have O1x is going to be in opposite direction. O1y is going to be in that direction. Just put it like that. So this is the same force, and the torque T2 is going to be like that. And then I have M2G here. And if I have some other forces on the payload of the robot, I will just put them here, right? So I could have like Px and Py, but we need to know these. These are not part of the inverse dynamics. All right, we need to know these forces. And again, I'm gonna do the same thing here. So this is that. What are the accelerations? I'm gonna do the same process basically. M2 AG2X, and I have M2 AG2Y. All right. We also have my RG2 alpha 2. All right. And let's put some angles on here. What is this angle? This angle here is going to be equal to what? Theta 1 plus theta 2, right? This angle right here is how much? Theta 1. Yeah, my resolution isn't that big on this camera, fortunately, but this is what I have. So alpha 1 theta 1 plus theta 2. This is angle here, and then this is the same angle on this side. All right, so we have a free body diagram. Now we need to find. We're trying to solve for what are the unknowns: OX, OY, O1x, O1y, T1, and T2. Okay. And what are the knowns? We should know the accelerations. Why? Because we know the angles, we know alpha, we know etc. We know all of this. So let us actually go ahead and basically solve this problem. So how many unknowns do we have, by the way, if we were to count them? Let's put them. Unknowns. We have OX, OY, O1x, sorry, what? The OX, sorry. OX, OY. OX, OY, T1, okay, and then on the second one we have O1x, O1y, and T2. So we have 6 unknowns. How many forces do we have? Or how many equations do we have? So on this link, we have one equation is something the forces in x direction. Second equation is something the forces in y direction, something the torque. So 3 here, and I have 3 here because it's obviously planar and then 2 degrees of freedom system. So we have 6 equations and 6 unknowns, and we should be able to solve these. Obviously, we're going to assume that we know AG2. We know all of these on the right side of in the inertial accelerations, in the inertial forces figures. Okay, let's go ahead and now find AG1x, AG1y. So one of the easiest way of doing this is we have two techniques, right? One of them, we learned it in our dynamics course, which is based on vector dynamics. Another one, which I'm going to introduce here, is simply based on differentiating the position, right? So all I have to do is I want to quickly come back here. I want to get the x position of G1, and then I'm going to differentiate that. I will get the velocity of the g in x direction, and differentiate one more time, we will actually get the acceleration. So let's write it here quickly. So what is xg1? Xg1 is equal to what? So you're going to try to simplify its x component, right? It's going to be equal to L1 over 2 cosine theta 1, right? How about yg1 is going to be equal to L1 over 2 sine theta 1. If I take these guys and then differentiate it with respect to time, I will actually get the velocity of g in the x direction. I will get the velocity of g1 in the y direction. And I can do the same process on g2. What is the value for xg2? Well, it's equal to the coordinate of this point, right? The x component of this point, which is equal to L1 cosine theta 1. Plus what? Plus this component, right? From here to here. So we're gonna basically sum these two, right? So this guy and this guy. So this guy is equal to L2 cosine theta 1 plus theta 2. Okay, and what is the component, what is the position of yg2 is going to be equal to L1 sine theta 1 plus L2 sine theta 1 plus theta 2. Okay, great. So this position is a multivariable function of theta 1 and theta 2, and then if I want to do like dx, I'm going to apply the chain rule of differentiation. So it's really nice and easy way of doing that. And then the beauty here is if you are using Matlab, basically you can program this in Matlab, and then you can quickly apply this technique. All right, so let me start by so we have xg1 is equal to L1 over 2 cosine theta 1. So what is dxg1? Is equal to dxg1 single variable d theta 1 multiplied by d theta 1 dt. So obviously here I'm dividing this by dt. So what is the partial derivative of xg1 with respect to theta 1 is going to be equal to minus L over 2 sine theta 1 multiplied by theta 1 prime. We know theta 1 prime. Why? Because we know theta 1 as a function of time. Now let's look into dy g1 dt is equal to dy g1 d theta 1, because it's only a single, it's only a function of theta 1 only. So we know yg1 was equal to L1 over 2 sine theta 1, so it will be simply L1 over 2 cosine theta 1 multiplied by theta 1 prime, right? So what is that, by the way? This guy is a g1x. So there you go. We have obtained a g1x, and then this guy is equal to what? A g1y. Now let's look into AG2, right? So very quick recap. So we have it all on one page. So we had xg2 is equal to L1 cosine theta 1. And by the way, if you're using the DH frames, you know how to get the position of any frame, right? And what you could also do, you could also actually put a frame at the center of gravity. And then you can find its coordinate that way, right? So this guy is a function of theta 1 and theta 2. So if I were to actually find the velocity here, so Vx g2 is, when I differentiate this guy, dx g2 with respect to theta 1 multiplied by theta 1 prime. Okay, so what is that partial derivative? So simply minus L1 sine theta 1 minus L2 theta 1 prime plus when I differentiate this guy with respect to theta 2, and then that will be minus L2 deal. Okay, last thing, so we're gonna find now the acceleration. So this is only velocity, so we need to actually find the acceleration. How do you find the acceleration? So now, okay, so if we want to differentiate this guy, so now this guy is a function. So let's put that again. So Vxg2 is a function of what? It's a function of theta 1, theta 2, theta 1 prime, theta 2 prime, right? So we introduced two new variables, right? Which are theta 1 and then theta 2 prime. How do you differentiate this function? So we're going to do it all over again, right? So let's quickly do that. So now we're trying to find the acceleration, right? Ax g2, right? So it's going to be equal to d Vx g2 with respect to d theta 1 multiplied by theta 1 prime plus d Vx theta 2 multiplied by theta 2 prime plus d Vx g2 d theta 2 prime up theta 1 prime, right? Which is this guy multiplied by, so d theta 1 prime dt is equal to theta 1 double dot. Now we have the acceleration plus d dx g2 d theta 2 prime multiplied by theta 2 double dot, which is angular acceleration of the same thing. Right? Okay, so we're here. So how do we do? So notice now we're basically converting this dynamics problem into more like a mathematical problem, right? And then we're doing it that way. So a x g2 is equal to, what is the first one? What is this guy? dvx d2 with respect to theta 1. We want to differentiate this whole thing with respect to theta 1, right? What would that be? So this guy is going to be the first component is going to be equal to minus L1 cosine theta 1 minus L2 cosine theta 1 plus theta 2. Simply it multiplies theta 1 prime. So we're good with the first one, right? So this will be simply differentiate this component. This guy is a constant right now, right? Because you're doing a partial derivative. Now, what is the second term? Partial derivative of this guy with respect to theta 2. So this guy will not with respect to theta 1. Okay, so we're missing, so we still have this term, right? So the partial derivative of this guy with respect to theta 1. So this is the first part. And the second part, we also have minus L2 cosine theta 1 plus theta 2 prime. Okay, now we're done with the first one. And notice, so this whole thing is multiplied by theta 1 prime, right? So we have to put a parenthesis again here, multiplied by theta 1 prime. And, you know, those of you who can try to see what is happening here, so theta 1 prime multiplied by theta 1 prime, this is actually your centrifugal component, right? Centrifugal acceleration, theta 1 prime squared, so we have some other combined, you know, dynamics is happening here. So let's do the second term plus scroll up a little bit on the page. Okay, there we go. So hopefully the source shows everything. So the second term is the partial derivative of the velocity with respect to theta 2, right? So here we don't have theta 1, we only have theta 2 here. So it's going to be minus L2 cosine theta 1 plus theta 2 multiplied by theta 1 prime. Second one will be minus L2 cosine theta 1 plus theta 2 multiplied by theta 2 prime. And this whole thing is multiplied by theta 2 prime, right? So this whole thing is multiplied by theta 2 prime. Okay, which is this guy. Now the third term is partial derivative of bx2 with respect to theta 2 prime. And it's easy here if you see that. So only when I differentiate this guy with respect to theta 1 prime only. Theta 1 prime, I'm just going to get this guy, okay? And then this guy here with respect to theta 2 prime, I'll just get this guy, right? Because it's partial derivative. Okay, so the first one is going to be simply this multiplied by the acceleration plus this multiplied by the acceleration of the second term. So just let's minus L1 sine theta 1 minus L2 sine theta 1 plus theta 2 theta 1 double dot. Last term is minus L2 sine plus theta 2 double dot. Okay, so luckily we have Matlab, and I think now you are beginning to appreciate why we actually need Matlab, right? You will not be able to progress or innovate a lot without actually having, the ability to, quickly manipulate variables and then visualize them and plot them and simplify them. Okay, so obviously we can do this in Matlab, and then as an exercise, I will let you guys do AYG2 and confirm it with Matlab. Okay, you must be able to do that. Okay, so this is an assignment for you guys, which I may ask, by the way, for in our second midterm, which is upcoming actually in November. I'm going to be sending you guys some more formal information, but since you all must be watching these lectures, it will be on it will actually be on Monday, November 7th. All right, Monday, November 7th, and it will cover all the work that we did on Jacobian, and it will also cover the inverse dynamics. So make sure you are watching these, you are kind of following up tightly on what we're doing here. So now, guys, we have the accelerations, and we are good here. So last thing that we do is we're just gonna sum the forces, right? So we're gonna sum the forces that we have. So back to here. So we're gonna sum the forces in the x direction, y direction, and then z direction, and put it finally in form that we can see. So summing the forces in the x direction on the first link 1. So we have to organize it like that. So what do you have? Okay, we're gonna have OX, right, plus O1X is gonna be equal to M1 AG1X. Okay, we already know AG1X. Then you're gonna sum the forces in the y direction, and you're gonna get what? OY minus M1G minus O1Y. Because I'm summing the forces in the vertical direction, whatever that you do on the left figure, you also must do on the right figure. So if I'm summing the forces in the vertical direction, I'm going to get M1 AG1Y, right? It will be M1 AG1Y. Last thing that we'll do is we're going to sum the torques, right? And again, whatever that you choose to sum your torques here, you need to sum them up. The same point you have to use the same point on this figure too. So if you sum the moments about this point and you assume counterclockwise in the positive direction, you also have to do the same thing here. So usually you want to choose a point where you can try to cancel as much unknowns as you can. So I want to choose this point. I'm going to choose the center of gravity. So I'm going to sum the moments about G1, and I'm going to use my counterclockwise from a positive direction. If I do this, I'm going to end up with what? So OX, right, basically multiplies the distance of L1 over 2, right, sine theta 1. And OY is in the opposite direction. So OY, L1 over 2, and I believe this should be cosine theta 1, right? MG will create no moments. Now I'm going to O1Y. So O1Y is in a positive direction. L1 over 2 multiplied by again cosine theta 1, and OX will be in the opposite direction, minus O1X multiplied by L1 over 2, and this would be sine theta 1, plus we have the torques. So we have torque 1 minus torque 2 is equal to G1 alpha. So this really captures the full dynamics. I'm gonna quickly redraw this so we see it on the figure. So we have OX, OY, O1X, O1Y, MG, T1, T2, right? And then this is my theta 1, right? So O1X is creating a positive moment, right? So this is the sign of the moment, right? So O1, so about this point, O1 is trying to create a positive rotation, right? This is why I have positive sign before that. O1 is actually trying to oppose this motion. If this was my positive direction, O1 is trying to create a clockwise moment, which is equal to OY, right, multiplied by L1 over 2, this distance, cosine of this. So this is a moment R for O1Y, right? So this is a moment R for O1Y, right? Okay. And again, here we have O1Y is creating a positive moment, right, in that direction. So L over 2 multiplied by cosine theta. So this is the moment R for O1Y. That is it, right? Okay, guys. So probably most of you have taken that in statics, but make sure you really understand how revise your notes for dynamics course, how we did all that. It's pretty self-explanatory, and then if you apply this, you will pretty straightforward how you understand the direction of the what moment is each force basically creating about a particular axis. And whatever that we did here, basically you also have to do it on the inertial figure, right? Basically, this is Newton's second law is summarized by this figure and that figure, right? So these forces are equal to these inertial forces, or these MAs in a sense, right? So here we sum the moment about G. The moment arm for M1 AG1X is 0, right? Because it actually is at the center of gravity. It's an inertial force at the center of gravity. Okay, so these are our first 3 equations, right? And then second 3 equations, basically you have to do the same thing. So on link 2, I'm gonna sum the forces in the x direction. And I'm gonna have minus O1x plus px, if I have some other force, is gonna be equal to M2 AG2x. And then you have to sum the forces in the y direction. You're gonna get minus O1y plus py is equal to M2 H2y, and then finally we're going to sum the moments in this direction. We're going to have T2 minus M2G L2 over 2. Well, wait, M2G, this creates no moments, right? Why? Because we're summing the moments about G2, correct? Okay, so we're gonna have T2 minus, so O1x will create a negative moment, O1x, L2 over 2, cosine theta 1 plus theta 2, right? So this is my O1x, O1y will actually create a positive moment, O1y multiplied by L2 over 2, cosine theta 1 plus theta 2, and then we have px, right? So px is creating a negative moment, so px L2 over 2 multiplied by sine theta 1 plus theta 2. Finally, we have py, I'll just put it upward, plus py 2 over 2 cosine theta 1 plus theta 2, and this whole thing is equal to ig2 alpha 2, which is theta 1 double dot plus theta 2 double dot. Okay, guys, so this is it regarding, doing inverse dynamics. So, you still have to do one step basically, which is putting these in matrix format. This is a bit complex, so usually I wouldn't, make you like do all this on an exam, obviously. But I highly recommend that you guys, try to embed this in Matlab and, put it in matrix format basically. So the matrix form would look like this. So what are the unknowns here? The unknowns are, we have OX, OY, T1, then you are going to have O1X, O1Y, and then T2. And then here you have your accelerations, all right? And then so as a result of this, basically we can do all of that. So I'll just do it for the first lane. So how would that look like? So we have O1, OX is 1. Okay, so I'm gonna do it here. So OX is 1. OY does not exist. T1 is 0. O1x is 1. O1y is 0. T2 is 0. So this is the first equation is equal to how much? Is equal to M1 AG1x. Okay. Second thing is you will do it, what is a component of x in the second equation? It is 0 basically. OY is equal to what? 1. T1 0, O1x 0, O1y minus 1, T2 0. On the right diagram, what do we have? We're going to have M1G plus M1 AG1y. Okay, so this is the equation on, this is the first link here, and then this is the second link. Oh, sorry, this is the second link. So this is a, first link, first equation, summing the forces in the x direction. So here we sum the forces in the x direction. Here we sum the forces in the y direction. Here we sum the moments. You write the equations here in matrix form, then you can simply solve that. So this is inverse dynamics. Any questions, guys? Please do contact me, send me an email, and I'll be very happy to jump on a Zoom call and explain to you anything that you are not understanding.